my students. So I thought I would model how I do this. And so one way to do it is to share another feature, the drawing feature. So I would ask my students a question, it could be about how do you feel about molecular shapes and polarity, and I ask them to draw it. Universal Design for Learning says multiple means of representation, multiple means of engagement, multiple means of expression. And so this is one of those multiple means. So I would like you to draw, and this will give you some practice on how the students would what their end looks like, and to use some of the features of Nearpod to draw how they feel about a concept, or to draw a molecule. Even you could ask, what do you think the water molecule looks like if it has two bonded atoms and two lone pair? And then they could draw it. So I'll give you a moment. I thought this would give us a good laugh too. Draw how you feel about teaching during COVID. Not only give us a good laugh, but a well-needed break from my talking. And then again, you get to experience, boo, you get to experience the features that a student would experience. Look at this. This is so talented. Okay, some of you are using the paintbrush, some of you are using the paint can, the spray can. And so this would be good to draw molecules even. Oh, wow. I love these. And they can take photos as well with this program. And so we'll give you some more time. Okay. So let's take a look at some of your drawings. Okay, people falling asleep. I usually let my students elaborate if I can't understand it. And look, a chemistry book or an assignment is burning. Okay, good. This looks pretty happy. Sleepy. Okay, frazzled. Uh, hello, can you all hear me? Any volunteers? Yeah. And I hate when my students don't put their videos on, because I tell them that 90% of communication is body language, and I can't tell if you understand or not if I'm just looking at your name. So these are some, oh, someone's sleeping. That's a great drawing, by the way. These are beautiful. Okay. This is crazy. Asking questions. Oh, I love this. Frazzled and tired. Oh, this is great. Is that someone's cat? You do. I feel like I'm teaching to sometimes they're pets. Let's see what else. Raining, sleeping, arg. When a teacher is asked to reflect on their time during distance teaching, I can't read that small print there, but I will be able to once I put it on the big one. So let me just, there, arg. Okay, so again, what's this? This one's over it. Okay, optimistic, good, good. Okay, okay, so this is the crest and this is the trough. That's right. Ups and downs, crests and troughs. That's a great way to look at it. Boy, you science people are creative. So that's just a feature that they can use during your class. And I find it really great for drawing molecules. So I just wanted to do something for us to give us a good laugh. And now let's move on to my next slide. Okay, and in my next slide, I'm going to go to the experts. I'd like you to put something on our shared board. These are like little stickies. How you engage your students. I shared a couple of things with you. My students love breakout groups because they yearn for connection. And when they go in the breakout groups, they can talk, you know, outside of chemistry as well and forge relationships that way. I play music. Let's see, what else do I do? I I I try to make it personal. When the cat is on the lap, I take a moment and ask the cat's name. So there are little touches, little things like that that they like. I told you about adult show and tell. My students uh, would just love, yeah, having joke time. I love that idea. Focus my cell phone camera through the objectives of my microscope. Good. Okay, and so they're popping up as you write them. And so you'll have access using Pear Deck. It's very similar to Nearpod. And Sam is going to be using Pear Deck later. So if everyone could just pop up some, yeah, relate topics to everyday life and interests. And I do that. Pear Deck, I use Pear Deck. Pear Deck is super popular. Some experiments that students can do at home with the camera on, collect data, compilation and analysis, competitive games. I love that. Zoom polling. I use Jeopardy for my competitive games. Using deck of cards with students' names on them to call on them. That's great. I kind of wish it was like um, that game where the different cubicles light up and they do it randomly. So yeah, I enjoy that too. Breakout rooms, use my phone as a document cam to show around the room when they're at home. That's a great idea. Some of the students might not want to show where they are, but that's okay. Check-in time and chemistry fact of the day. Oh, I love that. As a matter of fact, you could make the students come up with a chemistry fact of the day that interests them. Kahoot, I love Kahoot too. My students told me they were Kahooted out though. I used it so much, but it is a lot of fun. Ask students for topics that they would like to know more about. Absolutely. And aren't most of these or a lot of these things that you would do in person as well? Quiplash. I am not familiar with that, but hopefully you'll share it with me today. Cool chemist bios. I love that. I do a lot with female chemists as well, female scientists, minorities, breakout rooms, and weekly would you rather question. That's cool because when you ask questions like that, kids realize that they care, that you care about them. And I don't care what grade you're working with, whether you're working with seventh graders or college students, they want to feel like you care about them. So I like the what would you rather questions. Quizzes, I'm not familiar with that. Current events in Chem, such as they search events in the class and then put in on a Google slide and we share before the end of class. I love these ideas. So I am really finding virtual teaching wonderful. I am finding my students are acting more like scientists without me. And a lot of you might feel the same. I know that I love when my students' experiments go wrong because they learn more trying to figure out what went wrong than if they just get it right. So these are all wonderful ideas. And it's just like a sticky board that you can use. And then at the end, you get an Excel spreadsheet with everyone's comments on it. So it's really nice to have. And again, I asked this question. If we were in person, I would say, how do you engage your students? And maybe I'd pick on 3 or 4 of you. Well, guess what? In this virtual age, everyone has time to participate. Everyone can just pop up their thoughts on. So I think students are being held more accountable and more engaged with programs like this because they're all responsible for commenting. And you don't have to read every comment, but you could pick a few out. And so thank you for sharing those ways of getting engaged. We have so much talent out there. I thought I would tap the experts, you, to get some of these ideas. Now, again, I know this is small on it. If I put it in Zoom mode, it does go larger, but you will get a copy of this. So people asked, how do you handle at-home labs and safety? So in my syllabus, I have this comment. It says, I understand that I am taking an at-home lab course and I am responsible for my own safety. If I am under 18, I will do my labs under adult supervision. So if they choose, and again, my school has the option of doing it at home, okay, or in person. Now, if they choose that option, they totally subsume the responsibility of doing things safely. So they have to work with an adult. Now, as far as my at-home labs are concerned, what I require is a digital scale for the at-home lab, and I'll share with you. Sorry about that. What it looks like. Okay, I don't know if you can see this in the image part. I have a little balance or scale. It is for jewelry, and it is able to measure, it must be able to measure 500 grams or more and go to the 100th gram. And so that
Michelle, you need to stop sharing the
the
screen
stop sharing the screen.
if you want us to see your scale.
Okay, so let me just. Okay, did my screen stop sharing? Okay, so if you have it on gallery view, you can see the small scale, the balance that I have. And so let me. Okay, so the digital scale that I just talked about, and it has to go to the 100th gram. A 10th gram doesn't work when you're using vinegar and baking soda for a lot of the labs. Again, because if it's only a 10th and you're looking for a very small amount, I found that only the 100th gram works. A digital thermometer, most of my students are using meat thermometers, and most meat thermometers, let me stop sharing. Oops, I don't have that with me, but most meat thermometers go from minus 40 to 232 degrees Celsius. So meat thermometers work. And the meat thermometer costs $10. My balance, I think I said, costs $35. Additional items as needed for various labs. They use copper fixtures that they can get at Lowe's or Home Depot, marble, vinegar, baking soda, etc. We also make sure they purchase a 100 milliliter graduated cylinder, and my school bookstore sells all of this. They also have to have goggles. So that's what they have to buy if they're doing the virtual labs, or if you're teaching high school, that's what they would need. Maybe your school could buy these and then just reuse them from year to year. All of these different pieces of equipment, really, it's really pretty cheap if you think about it. It's under $50. And when you think about schools using a textbook, a textbook could be $175, and you can use these from year to year, just as some schools might have students make sure that they borrow an iPad or something for virtual teaching. Same thing for this type of equipment. Okay. Okay, so again, for virtual teaching, I have found that my students are really doing and behaving so much more like scientists. It wasn't until virtual teaching did I realize that I do too much for my students. I'm constantly answering their questions, and because they don't have access to me as much, they're forced to seek some of their answers on their own. So I just wanted to share with you something that I use. I use a Google Doc, and for this particular lab, this was Avogadro's number and approximating the mole of, or approximating the size of an oleic acid molecule. I just went through the steps, the calculations, and they were all standing at their lab stations for the in-person labs, watching as I did this. And then so I just modeled how to do the calculations. And then for them, they shared all of their data because, again, they're standing at the lab station. So this would be for the in-person lab, but you could also do it for the at-home lab. If you create a Google Doc and I made every station share their data. So for this particular lab, this is for Chem 101 introductory course for nursing students. They take regular Coke and Diet Coke. They put it in water. They see that the regular Coke sinks, the Diet Coke floats. And so they heat it up, drive off all of the volatile substances and end up with a residue. They do the percent of residue in each of the sodas. Since Diet Coke has aspartame or NutraSweet in it, and aspartame or NutraSweet is about 100 times sweeter than Coke. So if you just, for the sake of easy numbers here, if Coke has 100 grams of sugar or sweetener, let's say it's 100 grams of sweetener in it, then Diet Coke would have 1. So then they see that the masses are different, and mass per unit volume is density. And if the mass, even though the volume is being held constant, if the masses of the cans of soda are different, then the density will be different. So for this particular experiment, they had to not only analyze their data, but they had to analyze the whole class data. So here they're going beyond what I used to do when it was just in person, like they'd analyze their data, but now it's so easy to look at everyone's data synchronously. This one was a density lab. Again, I tell my students, you have to be aware of personal error in your conclusion, instrumental error, and method errors. And so for this particular lab, it was the same lab. It was still a density lab. It was all done in at the same time. They determined the volume of a steel bar 2 different ways. They determined the volume by water displacement, and they determined the volume by measuring length, width, and height. And again, in the past, I've just asked them which method was better because they'd compare it to the theoretical method. And then now I can say which method was really the better method for the entire class. And so again, they're putting their data on a common doc, and then they're interpreting not just their data, but they're comparing how they did to the entire class. So I liken this to different independent chemistry facilities. Like right now, different facilities developing vaccines, different ways of doing it. How do we compare those? And then this last semester, I had someone in our school had COVID. And so we had to shut down for 2 weeks. And so for the in-person labs, I had to get 2 labs in one day so that I wasn't running behind. So one of the modifications I made was for the solubility lab that I usually do. I do solubility of potassium nitrate and alum. Well, I just had, usually each group would do a 1 gram sample, a 3 gram sample, 5 and 7 gram sample. We didn't have time for that. So each person just took, like, the person number 1 or at station 1 did a 1 and a 3 gram sample. Then the person at station 2 did a 5 and a 7 gram sample. Person number 3 did 1 and 3. And again, they get to see the variation in data as well. And then they do the graph and they find whose data was closer to the accepted value. And they can look at it and say who did the best in the class. So in the past, I would have each student or each group do their own solubility table. Now I'm breaking it down so that not everyone is doing all 4 samples. and still we're getting data that represents that our N, if you will, is so much higher. So I love this aspect of using Google Docs for all of us to enter our data, because then the conclusion is richer, has much more rigor, because they're not just comparing to the theoretical value and their work, but they're looking at the work of other independent laboratories, if you will. So that's one way that I use Google Docs. Another thing I just wanted to mention, especially for high school and middle school teachers, okay, for the Chem 101 class that I teach, it's primarily nursing students. Some of these students have never had chemistry course before. And so a simple density lab, you can ramp that up. So here's an example of a density lab that I did at home. So this is just an informal lab. Here's a student took stevia sweetened soda and a regular soda, and they saw that the densities were different. Here is a student. So all of my students in their take-home labs, they had to either videotape it or take 5 photographs. 5 photographs that represent what they were actually doing, not just of their equipment. So here they're determining the density of water in a very simple way. There's the balance that I've been using. The pennies. So they had to take 25 pennies and determine the density of the pennies, and I did not give them the theoretical value. So in their quest to determine what the theoretical value was, they had to go to the mint. And at the mint, they learned that pennies after 1982, of course, are zinc and copper before that. So they took a look at their pennies as well. So here's an example of the data that they, so this was part 1. This was for the density of water. Then they did the density of glass marbles, density of pennies, and again, this was just the soda. And so when you go to this student's conclusion, let me just see if it's up here. Okay, here it is. I determined the density of tap water, deviated, and they're even reporting where they're getting their theoretical values from. The density of glass marbles, 2.44 gram, which deviate from the accepted value of 2.6. And in that quest, they learned that there are all types of glass. There was flint glass, crown glass. So they were asking me, which glass should I go with? Well, look at your percent error. We don't know what glass it is, but you can make a good educated guess if you consider which percent error was the lowest of all of the glass. And then the density I measured for the penny was 7.2 grams per grams per cubic centimeter, which deviated from the expected value of 7.186. And then I can just make my comments, with sig figs, that's virtually identical. So I have found that my students are really doing a lot more research than when the labs were just in person. Okay, so let me go on to this next. I'll give you a couple of sample labs that I've been using. And the different degree of sophistication as well for some of these labs. So here's a lab example, specific heat capacity. I asked them to buy copper. If they didn't have copper, they went with marbles. And so this particular student did not look up different types of glass. But I did want to share with you like the kinds of photographs that they take. So here's another balance that they use, or another scale here. Here's the meat thermometer. It goes to the 10th place. So it has really worked out well. And this is what a typical lab in their lab notebook would look like. So, and then, I try to get them to only draw one line through it, but that doesn't always happen. And so, again, that was a specific heat capacity lab. If we take a look at this lab, this is another specific heat capacity lab. I just want to show you some of the photographs from my students. And it's interesting how they change and adapt. Like this student did not put the marbles in a beaker first. They just put it on this little tray here. You know, it looked like they were going to roll off until I realized that there was a tray there. And then just some of the equipment. This is her taking the temperature of them. This particular student, let's see, this was the student that realized, hey, there's all different types of glass. So, okay, so silica glass, it's 0.840, crown glass is 0.67, flint glass 0.53, and Pyrex 7.53. And then she predicted on the basis of density, again, additional confirmatory tests would be needed, but she went with flint glass because her percent error was the lowest. And so in the past, if I were in lab, I would give them, when I do copper, specific heat capacity of copper, I give them the specific heat capacity of copper. And then they write their conclusion on that. And now they're looking it up. So I'm really excited about, you know, the great opportunities that there are with virtual teaching, and the fact that my students have to do a lot of the thinking that I used to do for them on their own. So this is just an example of that. And then let's go to another one. So here's some more sample labs. So I wanted to walk you through what a typical class looks like when I am teaching in person. And so I would go to my Nearpod, and then I usually talk about, you know, what we're doing. In this case, that I was talking about stoichiometry. And so this is a wonderful way to engage students with real life examples. And I ask students, how do you think an airbag works? And so we talk about it, and then I show them this video. So this is all in Nearpod. Okay, so I'm not going to show you the whole video. I'm just going to skip through it a little just to give you a feel for what it's like to be in one of my labs. So let me just move this ahead.
Normally held in place by a magnet, but in a crash, it comes flying free, and it flies right into an electrical circuit that tells the car's computer to deploy the airbags. Airbags don't just fill with gas like a balloon blowing up. That would be way too slow. The gas that fills airbags is actually produced by a chemical reaction. The classic example is sodium azide, which is stable until it's heated. In a crash, a small explosive or heating element called a squib goes off and ignites the sodium azide, which decomposes quickly to nitrogen gas and sodium metal. That sodium metal could react with water in the air to produce corrosive sodium hydroxide, so airbag manufacturers include some other compounds to react it into sodium oxide and alkaline silicate instead. By the way, the technology we described is a little old school. Nowadays, most frontal airbags are actually inflated with guanidine nitrate, but it works on the same principle as sodium azide. You're creating a lot of nitrogen gas. And accelerometers have changed with the times too. They're a little more sophisticated than the ball bearing thing. Meanwhile, the nitrogen gas is totally harmless, being the main ingredient in, air. Just a small handful of sodium azide can produce 67 liters of nitrogen. And that volume of gas creates enough pressure to fill the airbag in less than 40 milliseconds. So, quick first law refresher, an object in motion stays in motion. So when your car hits something, it stops, but your body keeps moving forward. And if it keeps moving forward right into the steering wheel or dashboard, that's bad news for you. So the airbag is there to slow you down more gradually than a steering wheel would. But this rapidly inflating cushion isn't actually pillowy soft. The front face of the airbag moves toward you at between 150 and 250 miles per hour. And if you were to hit it while it was still inflating, that might be almost as bad as hitting the steering wheel. To properly slow you down, an airbag has to have blown up already when you hit it. So that means the accelerometer detects the crash, the squib ignites the sodium azide, the nitrogen gas is produced, and in 50 milliseconds, it's already blown up in your face and started to wind down. Between 1987
Okay, so that video is about 4 minutes long. So they would all be at their lab stations. We talk about how an airbag works. Then I'd show them the video. Then with every lab, I go through disclaimers and I tell them that there are assumptions inherent in every lab that we do. I talk to them about the gas laws. Obviously, this would be this particular lab I did before I did the gas laws. I did it in the stoichiometry section. And so we're not allowed to hand out paper. So we're not allowed to touch paper. We're not allowed to hand out paper. So this is the lab that they got. So they have this on their phone or on their laptop. And so this lab I just loved. And this was one of the most memorable labs, the student said. So here's the reaction that they went over in the video. And I tell my students we're just going to do a simulation of it. And the challenge is this. I give them 5 grams of baking soda and I give them 30 milliliters of vinegar. And so the challenge then is that they have to produce the most amount of carbon dioxide without going over 12 grams, including the zipper bag. So let's take a look at what this looks like. So here's their data table. And again, they would put all of this into their lab notebook. This particular lab was called a lab challenge. So I just let them do it right on the lab paper. But you have the mass of the empty zipper bag. You have the mass of the sodium bicarbonate that you're using, the mass of the acetic acid. And then this last column is the mass of the sodium bicarbonate and the acetic acid, the bag and the acetic acid. So they can't go over 12 grams in this column. And so here's what they're set up. Another thing that I wanted to add for safety. Before every lab, I set the lab up. That's a little time consuming. In the past, I had my students just get what they needed, but they're not allowed to cross paths. They have to stay as stationary as possible. So this is what a typical lab setup would look like for this lab. Okay, they had the baking soda. I dispensed the vinegar ahead of time. They had their 3 bags. They had their scoop and they had their graduated cylinder. Now, also how we adapted during COVID is that we created this bath. Every student has to be responsible for decontaminating everything. So when they come in, they would fill this up with soapy water and they were responsible for cleaning all of their equipment. And because they could not work with lab partners, we had to improvise. So each student is working by themselves. Now they had to put the baking soda and the acetic acid in the same bag. And that typically is no problem at all when you have a partner. Well, you don't have a partner during COVID. So we had to use a clip that I bought from a hair place to divide the bag into 2 sections, one section that had the baking soda in it and the other section with the acetic acid. And so that's just the example. Now, if you think about it, these students are all looking at this, right? I wrote, make sure the gap of the clip is beyond the bag so the vinegar does not creep over. So, I went through safety precautions. So there's the gap that I was talking about. So through the safety precautions using Nearpod, I take photographs of things to help them out. And then I make them take pictures. So they'll show me their photos and I want to make sure they're doing their calculations right before they go on. So they'll take a picture of their calculation and I get it in real time. And so this is what that looks like. So here's their calculations. And then if I click on it, I could see them and say, wait a minute, I think you're doing something wrong. I could just look at their data table. and I could go through every student's calculations and just look at them and give them feedback before they actually moved on. And so they were taking pictures of things as we were going through the lab. And so here are the pictures of their bags. So here is one student's bag. So this is hardly inflated at all. Okay, this student wasn't following directions. They didn't put the photograph in the right spot. So this one's getting some height to it. This one's getting a little more height to it. They're producing more carbon dioxide. And the reason I love this lab so much is they had to determine the limiting reactant and that which was in excess. And when you see the baking soda still in the bottom, okay, of the bag, then they have a visual of what excess is. It didn't dissolve, so it's excess, or it didn't react. Okay, so so here is someone else's. They're getting a little more carbon dioxide in there. Again, I just want, you can rotate these, but for the sake of time, I'm not. This is another student's samples, 1, 2, and 3. Again, another student, their samples. Here you can see the baking soda. So their trial 3 still has baking soda at the bottom, so that they know the baking soda is in excess. So it's a really nice lab. Again, this is a lot of bubbling and some baking soda. And this was the winning one. So it had the greatest amount of inflation to it. Okay, and this was the student who had the most carbon dioxide. And so here are his bags. So he did one bag and didn't get much from it, did a second bag, didn't get much from it, and then the third bag was starting to work through the calculations to see what the maximum amount of carbon dioxide he could generate without going over the 12-gram total. So that was a nice guided inquiry lab that the students just loved. Okay, so, and then this is just a photograph. This is in the lab doing the actual lab. And I already showed you that. So I'll stop right now before I go on. I have more to share with you, but Sam, were there any questions in the chat that I should be addressing?
Dave had a question.
Go ahead, Dave.
Hey, Michelle, just a quick one on your solubility temperature, the crystallization lab with the potassium nitrate and the alum. Do you have students start with cool solution and heat it up and then cool it down again?
Yes,
You do?
they cool
Okay.
it down. Yep, exactly. Any other questions? Yep, that's exactly how I do it. And then I laugh because then they'll be, oh, I missed the saturation point. Now I have to do the experiment all over again. And I just say, no, you don't have to do the experiment again. Just heat it back up. So just reheat it, drive it back into solution and do it again. So thank you for asking that. Any other questions? Okay. Okay, so let me continue on. Guided inquiry labs. So if they were at home, I'm really impressed with how sophisticated my students can get without me. And I love seeing them modify equipment to accommodate different labs. So I can either play this on my own device, or I could send it out to all of you to play it, but I'm just going to, for the sake of time, play it on my own device. I use a lot of science guy videos. And so let me just share this one with you real quick.
Use of goggles, temperature-resistant gloves, and an apron or lab coat to protect from spills and splashes. The first step in our experiment is going to be to blow up our balloon. Now, if you watched our previous episode, we're going to want to blow it up a little bit more this time. Like so. I'm just going to tie it off like so.
We used a full-size 12-inch party balloon and less water. We also placed a lid on the top to contain the hot air inside the beaker. In this version of our experiment, we see a more dramatic change in the balloon's size, as well as a much lower risk of the balloon popping. As it warms up, it will gradually increase in size. Let's look at this experiment a little closer. Charles' gas law states that when a fixed amount or mass of an ideal gas is kept at a constant pressure and in a closed system, then its temperature and volume are directly proportional. What this means is, when temperature increases, gas is a theoretical gas composed of under normal conditions, the higher temperature water and steam molecules.
So I just wanted to share that video with you, and this will all be in the resources. And so they watch the video, then they have to design the steps to the lab. And so for this lab, they had to make it a quantitative lab. The video demonstration is more qualitative. So I made them take that video and turn it into a quantitative lab. And let me share with you what some of the students did. Now, this was so cool because this was toward the end of the semester. And those students that really struggled, you could see the difference in their experimental design compared to the students that that really enjoyed the challenge and just ran with it. So I have samples of different student work. So if we take a look at this first one, okay, this student, you know, the Charles Lab, they don't have a graph or anything. They don't even have they took the diameter of the balloon only. They didn't seek out volume, or they just took the diameter. Now, do I feel that this student understands Charles' law? I do, because I talked to the student, first of all. I told them that they should arrange these from, you know, lowest temperature to highest. So freezer in the balloon, 32.1 centimeters, then room temperature, 34.3, then boiling water. So they're seeing that it goes up, but they're just using diameter to show that. So here are some of their photographs. This is a very rudimentary understanding. Now contrast this lab with this next one. Okay, so this student, okay, they did the background. They have to develop their own procedures. It doesn't say in the video how long to put it into the freezer. It says a couple of hours. So how long, take the you know, how long you're going to keep it in. So this particular student used 2 different balloons, and we talked about how that might impact the experiment as well. But notice this student also set out to use the actual formula for a sphere, 4/3 pi r cubed. And so much greater sophistication. And this student is an A student, okay, compared to the previous student, which is a C student. And so, you know, they used a you know, flexible measuring tape at home. Okay, and so I just wanted you to see, look, and you can see like what kind of ice cream they like, stuff like that. So that's one example. Now let me show you one more example. And so this student started off with the background information, and here's their lab. Now I like this because look at what students have to do to improvise. So if they didn't have a flexible tape, look, they designed their own. And so things like this give me goosebumps because I'm not telling them how to do it. When they're in lab, we have all the resources for them. So I love how creative they are in trying to figure out, oh, here's some eggnog ice cream, trying to figure out how to adapt the lab. And so, I mean, I think this was just so nice what the student did. This is before the heat, after the chill. So just really neat to see students be so creative and more scientific than me just handing out the equipment. So I really enjoy that. When we were home in March, I made up some videos myself, and I just said, this is a really rough idea of what you're doing. You have to turn it into a scientific lab. So just to give you an idea, let me just, so I tell them their assumption is inherent in every lab.
And then to give it contrast, I'm going to use Gravy Master. Ideally, I would be using food coloring. I don't have that. I thought, well, hey, you know, I could use some of this. This is cold syrup, but I don't want to use anything with alcohol. The cough syrup is red, so I thought I could use that, but then I looked and noticed that it has alcohol. Do not use anything with alcohol. So again, the sole purpose of the Gravy Master here is just to provide a little bit of contrast with the water. So I'm just going to spin that around a little. And as we mentioned, when you do this experiment, not only will you need a glass, okay, and again, I'm not using an ideal glass, but I'll show you a way around that. Okay, we need our candle. This is what we talked about prior to doing the experiment. Prior to any experiment, you need to write out your procedures. Okay, so we will then put a tea light in the middle there, and we are going to light that tea light. Okay, and we're going to let it burn for a while. Again, we said that oxygen was necessary for combustion. The amount of oxygen in this pint glass, okay, we're going to figure out the volume of this glass by filling it with water and then putting it into our measuring cup, our measuring glass, our Pyrex measuring glass. So, okay, now that we have a nice flame there, okay, we're going to, again, we have about 450 milliliters of air in here. The reason I know that is that I filled it up with water earlier, and I'll do that again today to show you, and I measured it here. So I filled it all the way to the top. So if I have 450 milliliters of water in here, if I take the water out, I have 450 milliliters of air. Okay, so now I'm going to invert it, okay, and we're going to get down a little further so that we can see what's happening. Okay, and you will notice, okay, that it will start to rise in the glass. There it is. Okay, notice that it pulled the outside water into the glass because we have a pressure differential. Okay, that pressure differential being that the oxygen has been consumed. Now again, there are many assumptions that we make in a full-blown professional lab. At a home lab like this, there are several things that will skew our results, but you can't be any more precise than your least precise. Careful than I have to pour this in. I just lost a lot. Okay, you won't do that because you'll be more methodical than I am. And then I will take the measurement on the side here. And I notice that I have 450 milliliters. Okay, so in any instrument, you can always read one beyond your least precise. Okay, I am just, okay, which really means I have 450 milliliters of air. Okay, now that I know how much this glass contains, I'm now going to fill it up to my marking. Okay, so I'm going to pour all of this in up to my mark. Okay, so now if you notice that gap right here, that's the amount of oxygen that was consumed.
So basically, I did a Dalton's Law of partial pressure very crudely. I had them design a the steps to it, and you get about 21%. And again, there are a lot of assumptions in that lab, but it's a simple way to have students do something at home that pertains to Dalton's Law. I also wanted to show you very quickly the PhET simulations are built right into Nearpod. So I chose the molecular shape and polarity because I know Sam's going to talk about Vesper. And I just love using this, you know, for molecular shapes and polarity. Students can add lone pair to it. You can see the molecular geometry. And again, right in Nearpod, you can select all of these different PhET simulations. So I can add another bond to it, and we have a pyramid-shaped molecule. Okay, and so there we go. There's my pyramid. Then you can take one off. You can put, let's take that off. Then you have your tetrahedral. Here you have trigonal planar. Put another one on. And now, and they can see that atoms seek to be as far away from each other as possible unless you have a lone pair to distort it. And they always spread out to give the point of least resistance. There are a lot of other things. There are some virtual field trips that you can do through Nearpod. The sharing resources, I will put this link into our chat box, and I will send it out as well after our session today. I'm trying to be cognizant of time here. This is like a virtual field trip. There's so many different ones that you can go on. That one's a particular museum. And now, so that I don't waste more time, I want to make sure Sam gets everything in that she wants to get in. And so why don't we just rate this part of the session? This part is anonymous. So then I'll turn it over to Sam. And one of the things I want to mention that